Did you get the code?
Mm-hmm.
Does it run?
I'm just opening MATLAB now.
Okay.
We'll find out. It runs.
Okay. So what does it do?
I've got a little Gaussian kind of jiggling back and forth.
How many?
One, it looks like Gaussian, and two potentials.
And how many Gaussians?
I mean, it looks like it's just the one, but there might be two in there. Oh, okay. Yeah, it looks like there should be two. One of them's just a flat line, so.
Okay, let me run to check. Is it really so? No, it's not a flat line. See, there is a little thing here. Red one.
Oh, my little thing that's bubbled up is blue.
There is blue.
Or at least the one that I can see.
Huh?
The one that I can see, at least at the end of it, is blue.
But do you see developments in the red line?
They might be covered by the potentials. I can run it again.
If it is not visible enough, we can just multiply and see what happens.
Oh, yeah, there's a little bit going on in the red.
Okay. So what are we doing? So, in many molecules and solids, the number of electronic states is larger than one. Okay. So if you have electronic levels, they all are occupied, and it is a ground state. But then you can excite it and promote an electron somewhere up. So two states, ground and excited. Okay?
Yeah.
Now, in addition to electronic degrees of freedom, there are interatomic distances. And the main idea is that if you look for, well, diatomic, but later the same approach can be applied to any system. So if you do have equilibrium and we want to draw a potential energy surface, or just V of R. you can tell that it is something like harmonic near the equilibrium position.
Mhm.
And we can tell that this is V of R for ground state. What would happen to this potential if we change electronic state of the system? Like if there is this h bar omega, h nu, we can assume that there will be shift of the potential higher up by the value h nu. Excited? Right? Like it's in zeroth order approximation.
Yeah. So I guess, okay, so are your circles representing protons or
Yes.
electrons?
Yes. Well, just atoms.
Okay.
Let's not specify them. Diatomic molecules can be like iodine atoms in a molecule. But so this would be correct in case electronic and nuclear degrees of freedom do not interact, if they behave completely separated. But there is a chance that while we are promoting from one electronic state to another one, the shapes of electronic clouds change substantially, and they may change their localization in space. For example, right now I'm not given very specific things. It's only like Gedanken experiment. In the ground, the electron can be equally spread over left and right of the diatomic, and upon excitation, it can migrate. So there will be excess of negative on one center and excess of positive, or lack of negative on the other one.
Mhm.
What would happen to interatomic force then?
It would increase.
It would become attractive. It will
Yeah.
contract them. So
Yeah, I guess technically the force then would be negative, so it would technically decrease. So pull it together.
if they become one positive, another negative, there will be additional component to the force that will
Yeah.
Put
Yeah, the
them
force will be stronger.
together. So then, if there is a plus and minus, then this line needs to be changed in the following way, so that the equilibrium position for excited state will be different from equilibrium position for the ground state. This is the very, very common situation, and no matter what is the nature of interatomic distances, how many atoms in the molecule, no matter what is the shape, is it purely harmonic or Morse potential or something very complicated and atomistically and maybe multidimensional. This idea is very general. So in the zeroth order approximation, change of electronic state just offset energy vertically, and in the next level there is a change of equilibrium position. If we dig deeper, then the shape of potential, the curvature may also change and other things. But shift of equilibrium is something that we need to take into account, whether we are physicists, chemists, or engineers. For math people, it's so big. So what is our problem? What do we need to do? Why it is interesting and important? before, and since there are not many people, you're free to stop and give your own opinion or change the direction of narration. So, anytime before this moment, in these labs, we were talking that there is a reactant, there is a product reaction coordinate, and chemical reaction would correspond to overcoming the barrier with kinetic energy. So this is a very good picture, and it works in 90% of chemical reactions when we know for sure that the system stays in the ground state. So bonds are broken or formed, but overall multi-electron, multi-ion system stays in the ground state. But here, if we do know predominantly that electronic configuration is changing, even making complicated one-dimensional potential is not sufficient. So we can move in two different directions if we want to be more and more precise in describing real world. One is modifying potential, make it multi-dimensional, multi-minima with some transition state. Or instead of going to these complications, we may admit that upon change of the electronic state, there is a just shift. And this approach can be quicker and more beneficial than doing all these complications. So it's an approximation, but it catches main feature. In our life in this class before, in this lab before, we were posing a goal to describe the yield and rate of chemical reaction. So if we develop the wave function, we integrate from center and tell that it is left, like probability that there is no reaction, and then we integrate from center to whatever, to infinity. And we take that it is probability for the product or right side. And then we can look how these things develop in time. Very good picture. Substantial number of chemical reactions can be described with this. But if we are not in this picture, how would we formulate our goals? So we need the probability of no reaction, and we need the probability of completed reaction. And then later we need rates of reaction, but maybe there will be no time for this today. And of course, we are posing the goals, but there is a question like, how would wave function look for these two potentials? In which of these potentials does it propagate? Should it be one wave function or two wave functions? You see, when you run the code, you see two wave functions, and they're kind of independent or dependent in a strange way.
Well, I know that you can superimpose waves, so you can treat them as separate ones.
Yes, but we do need to catch a probability that of transitions between two different electronic states. Because of different mechanism. It could be assisted either by a photon or a phonon. Like here we have transition assisted by photon. Light transmits electronic system from one state to another one. But same thing can be done by a photon. So by adding or removing vibrational energy may help to go between different electronic states, especially if the offset of the electronic states is not big. You feel the challenge. Well, we will address it, and we will be not first who did it, but it is next level of complexity. So I'm going to erase everything. Let's start over. There is no time for non-parabolic, non-harmonic potentials. So as approximation, we will think only of parabolas. Which will be characterized by curvature and equilibrium position. Ground, excited. And we do have two electronic states. Ground, excited. What should we do? Okay, for a few seconds, let's forget about vibrational degrees or nuclear oscillations. Just think about two electronic states. We are jumping very far in space of knowledge and a bit a week ahead of the class material. Like if you have only two electronic states, no matter what can and what should we do with them? If you want to predict future, if they already eigenstates of the Hamiltonian, and we want to, or maybe not. What is possible? How to treat two electronic states? So one can probably set up a Hamiltonian, which can be operator, and then put it in a matrix form, where elements of Hamiltonian will be how big will be Hamiltonian in a matrix form?
Just a 2 by 2 if we're
Yes.
only having the two states.
So whatever operator is, it is matrix elements in the basis of this grounded and excited state. So energy, if you know predominantly if it is in ground, energy if you know that it is predominantly in the excited. And then, since this grounded excited may or may not be eigenstates of the larger Hamiltonian, there could be off-diagonal terms, because we do not know if we have diagonalized it or not. Which the off-diagonal parts of the Hamiltonian, what are they? It's amplitude of probability of transition between ground and excited. It's how they are mixed. So if we diagonalize Hamiltonian, we always get rid of off-diagonal elements, but then they mix the initial basis states of diagonal mix basis states. Or if you are thinking in the time resolved picture, you can tell that it is amplitude of probability for transition. Between ground and XA. No objections. Okay, I'm going to erase and start over. How would we write down the Schrodinger equation for this Hamiltonian? Is the more general, the time-dependent Schrodinger equation? And how, well, even before Schrodinger equation, how would we write general wave function for system in this basis? Right?
Yeah.
So
yeah.
expansion coefficients in the given basis, and if the states are not predominant the eigenstates of the Hamiltonian, or if the Hamiltonian is of diagonal, these coefficients can be time dependent. Right?
Mhm.
If they are eigenstates, then Hamiltonian should be off, should have no off diagonal elements, and then nothing would change with time.
Right.
So instead of writing wave function in general form or as, well, basically two numbers. So we can write it as C ground T, C excited T. Right?
Mm.
So wave function is the vector in two-dimensional space. What is Schrodinger equation?
You're asking for like the
Verbal,
wave
not
equation.
writing down, but philosophically, what would be Schrodinger equation doing to this elements of this vector?
Be taking the derivatives of them with
Yeah.
respect to space and time.
Right, no space, because we are already in abstract space of this two dimensions. So it's instead of infinite number of degrees of freedom, it's only two.
Yeah.
It's discrete. Trajectory.
Right.
How does wave function changes in time? Something acting on right?
Yeah.
What will be here in the which
The-
matrix?
The Hamiltonian.
Yes.
Shouldn't your indices be swapped around? Well, I guess because you want to start with your ground state, right, in the top left.
But yes, you're correct. Thank you. Happy about this. Okay. Can you apply here our baggage of knowledge? can we solve this? Well, can we solve this equation in symbolic form? Like write C, G, C, E of time equals something.
Yeah. Well, yeah. We can do
This we can put here in the evolution operator.
what the evolution. Wait, isn't that just like a?
E to the power Hamiltonian time times time.
Yeah.
Right? So big exponential in the power of matrix. Put matrix as the power of exponential, with understanding that e to the power something is 1 plus something squared over 2 plus so forth, right?
Yeah.
And then this will be a matrix, 2 by 2 matrix, which will act on the C ground of 0, C excited of 0, and give C, let's put here delta t to be conservative, C ground of delta t, C excited of delta t. Okay?
Mhm.
So we can propagate two-component, two-level system wave function forward in time with evolution operator, and maybe borrow some methods from our previous experience here in the lab. Okay, I'm going to erase. Do you still have steam? We will not go longer than typical, maybe even shorter, but I just want to see that you are not like falling asleep.
I'm doing all right now.
Huh?
I'm doing all right now.
Okay,
Got a little nap in after class.
that's good. So suppose that yet we do not have nuclear degrees of freedom in our head. We were talking for time only about electronic degrees of freedom. Well, the rates that we need to get paid can be expressed as C ground of T absolute value squared will be probability of no reaction of T, and the C excited of T absolute value squared will be probability that by time T the reaction has completed, right? Good. Complete by T equal by T. Prepare. I'm going to say something that is dangerous, that can throw mind off. Ready?
I'm ready.
Comma R, comma R, depends on R, depends on R, depends on R, depends on R, T, comma R, T, comma R. This is really useful in practice and dangerous for thinking. So how can we interpret this equation? How do you interpret it?
Well, I mean, you're saying that the state of the wave depends on the position as well now, which, I mean, I don't know. It seems like that shouldn't be the case because it basically.
It is the case. We can, before we may, in previous years, when colleagues were attending my class for evaluation, they were telling that my biggest place is that I do not organize information linearly, and narration goes like from right to the left or from bottom to the up. I cannot resist and will do it again. So remember this picture we started from. R potential. So right now we have, before this mind throwing step, we have fixed and told that R is equal R ground equilibrium as a constant. So we do not, we have frozen nuclear degrees of freedom and we do not allow interatomic distance to change. So basically we solve Schrodinger equation with giving no permission for atoms to move, like below 0 Kelvin. Well, at 0 Kelvin there is zero vibrations.
Right. Yeah.
So it is something like classical 0 Kelvin. So we nailed down. Nailed position. And then we have probability that the system is in the ground and probability that the system is in the excited. Or this would be H ground, H excited, and if they have probability transmission, it will mix them, right? Of R equilibrium for ground. Right? So when we were speaking about two-level system, we intentionally forgotten about nuclear degrees of freedom. We like issued a decree. Hey, nuclei, we forbid you to move. Therefore, we got this simple thing. But now, we must admit that it is hard to issue such a decree. And the nuclei would move anyway. Then we have infinite number of two-level systems for each interatomic position, each of which would evolve according to this equation. Therefore, it is parameterized by R. Express your concerns. It's better to do now than later.
So you're just saying that we have a different equation for each position?
The expansion coefficients would be position dependent.
Yeah.
And the Hamiltonian will be position dependent. As you can easily see here, if we move to the right, the energy offset between ground and excited will be smaller. If you move to the left, it will become bigger. So the energy of excited state will be different depending on at which position we are exploring the system. Okay?
Yeah.
Happy, or at least not too many protests. I'm going to erase it and surprise you once again.
Sounds good.
Huh?
Sounds good.
Okay. It's just no space. I'm going to erase and rewrite this equation once again. Almost in the same shape. C ground T exponential minus I h bar of a matrix. Matrix C ground of 0, C excited of 0. Can we explicitly write down the dependence of the Hamiltonian on the position? Yes, it's just parabolic. So it will be m omega squared over 2 r minus r ground squared. Here it will be m omega squared over 2 r minus r excited square. And since we have additional offset, even if they are coinciding, there is a frozen offset, like delta out of delta that would be contributing to them at origin. Another parameter that would offset parabolas in the y. In case we do not have nuclear degrees of freedom, the Hamiltonian will be like 0, delta E, 0, 0, right? Energy of ground, we can always shift it to have it 0, and then it is energy of excited. If we do have non-zero transmission probability, you can put it as coupling. Right now we are not discussing the origin of coupling, we will just take it as the constant, just to make our life simpler. But there is a very exciting area of knowledge with finding these couplings and discussing where they originate from. So we will assume that couplings do not depend on position, and this there is offset. So we have I'm repeating the same square 2 ground squared square 2 plus r excited squared e. So to some sort it is mixed discrete and continuous representation. So it is discrete in respect to electronic degrees of freedom and continuous in respect to nuclear degrees of freedom.
Why is it continuous with respect to nuclear degrees of freedom?
Because we continuously change position.
Okay.
And the way, I do not have words to tell about it, but the symbols speak for themselves. Expansion coefficient of wave function over ground electronic state depends on position and time. So it's basically same as wave function in one-dimensional continuous problem, right? Non-free space, because space with some potential. Here it is like, again, wave function that depends on position and time. But when we want to learn the future, these two wave functions would propagate under influence of different potentials. So if we remove couplings, this wave function would perform oscillations around the R sub G. This wave function would perform oscillations around R sub E, if you initially set up them to be non-zero. happy or unhappy you are.
Kind of in the middle ground, I guess.
Okay, let's make a little break and watch the movie once again from the point of view of this knowledge. Can we I don't know where the receiver is, and I don't know where to point. It's camera, but the actual receiver may be under this table because most of the equipment is there. Ah, it's easier for me to move this thing here. So there are two potentials, and originally we set up the wave functions. So blue and green is wave function squared for this C sub G and C sub E. So originally it oscillates near equilibrium of the first parabola, and then since there is a non-zero transmission probability from blue to red, there appears a little bit in the second parabola. And then we are processing it by finding overall probability of no reaction as function of time and probability of complete reaction as function of time. There are two lines because we have two methods for momentum operator. So initially all probabilities in one parabola in one electronic state, and as time passes by there appears non-zero probability that reaction has completed by whatever 5–10%. And you can see this is not continuous change. The oscillations give kind of stepwise character of the reaction. So when it approaches to their intersection, it goes a little further. Okay, let's scroll through the code a little bit.
Oh boy.
So we do, let me point several things. The Hamiltonian is matrix 2 by 2. But each element of the matrix does depend on the position. So here is this matrix 2 by 2, and we again can use abbreviation HAM for Hamiltonian. And here abbreviations are up and down for like ground and excited. Yeah. So up, well formally I should write up, up and down, down. Yeah. So it is for one state and another state, which would be, we will scroll and see that they are modeled as harmonic potentials with different offsets along position. And those would be constants times identity matrix. How would we record the wave function? We need, it's a rhetoric question, I know the answer. So we need twice as much space. So we can either use two different arrays, two different variables for wave function in one electronic state and wave function in another electronic state. Or we can use the same array of twice the size and store one electronic state in the first half of array from whatever 1 to number of points along position, and then another electronic state in another part of array. So for one electronic state and another electronic state, it is same as we did before, kinetic energy plus potential, kinetic energy plus potential. So the only difference between them in potential that defines parabola, how it is shaped, where it is centered, and the offset on the vertical transition. So kinetic energy is not affected, and those are just NA. It doesn't mean not applicable. It means non-adiabatic. For transitions between electronic states, so nuclear motion assisted transition, times the identity matrix. So where do we define the wave function?
Wait, it's
Huh?
you're defining your matrix to have elements that are matrices?
So we define the wave function that has two components, one for electronic, another for one for ground, another for excited, or one for up, another for down. We can store them in the same data set back to back. So these recordings, which will mean that we have all, whatever, 100 elements for one wave function, and then in the same array, another 100 elements for another one. So just for programming effort, it's you can reprogram a different way, but in this way it is a little shorter overall coding. And then the initial just a second. So we need to scroll for psi up and psi down. So here, for one, that is in right now we are looking for a transition from excited to ground, which is maybe energetically favorable. So we set up the wave function in the excited state equal to Gaussian wave function, same way as we did before. And for the one in the second electronic state down, we just multiply it by 0, so there is nothing, completely 0. Not just Gauss in a different position, 0. And then when we need to look for probability, we just take one part of the array, integrate it over space, and look as it depends over time. Good? What else? What else is not ready? Basically, you got the main idea, right?
I believe so.
There are technical details. So there should be evolution operator that takes exponential of this Hamiltonian. And then there are technical things. How to prepare parabolas, potentials, how to prepare initial state, which we did before, and how to analyze results. So I will quickly go over it, but we shouldn't overwork. So two potentials, up and down, and we determine them by curvature times square function offset by different equilibrium points. And one of them is offset by this delta E. So what else is important? Right now, the parameters are arbitrary. But if you want to model practically important things, we need to either guess, do some calculations by hand, read the literature, or do ab initio computational chemistry data to find equilibrium position, which in fact a standard problem. So you optimize geometry for ground, for excited, and then you get the interatomic distances. So here the positions are 35 and 45 in atomic units. So they are offset by 10 atomic units, which will be how much in angstrom? Twice less, like 5 angstrom. Too many. Typically, when we are talking about nuclear reorganization, change of equilibrium position, we should speak about fractions of an angstrom. So the overall space for simulation cell should range a little bit to the left and to the right from typical interatomic distance. Like the center is 2 angstrom, and then plus minus maybe 30%. So from 1.5 angstrom to like 3 angstrom would be enough. Because if you do not have bond breaking, then it will be very close to such things. Another aspect is that so it's something that we didn't do before. This is very rough, but correct by order of magnitude. So it's literal data are not practically applicable, but before mass was equal to 1 for electron. But here we are talking about nuclei. Even the lightest nuclei, the proton, is 2000 times heavier. And if we are looking on the very high inertia, very heavy objects compared to electrons, the time scale is much different. So the parameter that determines the time step should be taken longer. What was the value of tau when we were playing with electrons?
I want to say it was like a single digit. Like
yeah, of the order of 1.
Yeah.
So now, if we increase mass, we can also make much more sparser time steps. Okay. So, if you have already everything ready for your project, and your project is different from this, but if you would do something like this, what would be your steps? So,
It's like time steps, or
no.
Okay.
Practical steps to do the research.
Well, I guess I would have to figure out what to set those values to.
Right. So offset, curvature, and equilibrium position of parabolas. So this is input data without which we cannot process further. There is another comment I really wanted to give, and so instead of propagating it this way, one can do at each position, one can diagonalize this 2 by 2 Hamiltonian. And then this set of two parabolas that intersect would convert into two sets of potential energy surfaces that do not intersect. And the lowest one would be a double well potential that would correspond to moving in the ground adiabatic state. So the height, you see, it goes a little bit up and then down. So this height is activation barrier that is clear energy of activation, that is very clear concept for anyone with chemical background. So one can describe standard reactions with this picture as well. So it is more general. Reactant, product, activation energy. I suggest I'll stop presenting, maybe even stop recording, and then we either stop it completely or I will stay and play by putting some more realistic numbers. But it is, it will be too heavy if we do it in the recording. So this was intense hour. Objections?